Picture this: a ghostly atmosphere stretching 696,000 kilometers across space. That's not the diameter of a star or a gas giant. It's the invisible envelope surrounding what might be the most extraordinary visitor our solar system has received in decades. Right now, as you listen to these words, Comet 3I-ATLAS is racing toward the Sun, dragging behind it a carbon dioxide atmosphere so enormous it could swallow our entire star. The Spherex Observatory has mapped this spectral giant, revealing a coma, that's the technical term for a comet's fuzzy atmosphere, extending at least 348,000 kilometers in every direction. Do the math, and you're looking at something roughly half the Sun's diameter in width. But here's where it gets interesting. This isn't some blazing inferno you could spot with backyard binoculars. The comet's nucleus, its actual rocky heart, remains frustratingly small and dim. Hubble's best estimates place it at no more than 5.6 kilometers across. That's smaller than Manhattan. Yet somehow, this cosmic pebble is generating an atmosphere 55 times wider than Earth. The question that's keeping astronomers awake at night is simple. How is this even possible? And more unsettling still, what does this impossible visitor reveal about the terrifying scales on which our universe truly operates? Stay with us as we unravel the mystery of 3I-ATLAS, because what we've discovered about this ancient wanderer will change how you see the cosmos forever. To understand how something so small can create something so impossibly large, we need to look at what 3I-ATLAS is actually made of. The answer lies hidden in its alien chemistry. While most comets we're familiar with spew water vapor when the sun's heat reaches them, 3I-ATLAS decided to be different. It's belching carbon dioxide at a rate that would make a soda factory jealous. And carbon dioxide, unlike water, starts sublimating, turning directly from ice to gas at much colder temperatures. This means 3I-ATLAS began its atmospheric show while still incredibly far from the Sun, building that half-sun-wide envelope we're witnessing today. Think of it as the solar system's most extravagant magic trick. A tiny performer creates an illusion so massive it defies our understanding of scale. The coma isn't solid, of course. It's more like cosmic fog, a tenuous collection of gas molecules expanding into the vacuum at speeds that would liquefy any earthly atmosphere. But its sheer size creates problems we've never had to solve before. Take photography, for instance. When astronomers try to capture 3I-ATLAS, they're shooting through some of the densest star fields in our galaxy. The comet's trajectory carries it across the Milky Way's most crowded regions, turning every observation session into an exercise in stellar hide-and-seek. Images streak with star trails as telescopes track the comet's motion, creating pictures that look more like abstract art than scientific data. The carbon dioxide shows up best in infrared light, invisible to our eyes but crystal clear to specialized detectors. In these wavelengths, 3I-ATLAS resembles a glowing soap bubble drifting through space, its edges so faint they blur into nothingness. The visible coma, what you might actually see through a telescope, is much smaller, perhaps only 26,000 kilometers across. Still massive by Earth standards, but a mere fraction of the infrared monster lurking beyond. This disconnect between visible and invisible scale should make us uncomfortable. How many other cosmic phenomena are we missing simply because we're looking in the wrong wavelengths? How many half-sun-wide atmospheres have drifted past unnoticed because they don't glow in the colors our ancestors evolved to see? The carbon dioxide envelope tells us something profound about 3I-ATLAS's origins. Most solar system comets are water-rich, reflecting the conditions where they formed in our Sun's protoplanetary disk. But a comet this rich in carbon dioxide suggests formation in a colder, more distant environment, perhaps around a different star entirely. We're not just witnessing a large coma, we're seeing evidence of alien chemistry, literally. As 3I-ATLAS continues its approach toward October's closest encounter with the Sun, that already enormous atmosphere should grow even larger. More heat means more sublimation, more gas production, more expansion. The half-sun-wide envelope we see today might be just the beginning. But here's the truly unsettling part. The size of the coma determines how the comet interacts with the solar wind, that stream of charged particles constantly flowing from our star. A bigger atmosphere means a bigger target, more dramatic interactions, more opportunities for the kind of space weather phenomena that can disconnect comet tails or create spectacular light, shows millions of kilometers long. The stage is set for a performance measured not in theaters or stadiums, but in astronomical units. 3I-ATLAS isn't just visiting our solar system, it's transforming a region of space larger than our Sun into its personal laboratory. And we're all invited to watch what happens when half a sun's worth of atmosphere meets the full fury of a star at solar maximum. Part 2. A hyperfast ancient traveller. Speed kills, they say. But in the case of 3I-ATLAS, speed reveals. This isn't just another comet lazily orbiting our Sun like a cosmic commuter on a predictable schedule. 3I-ATLAS is moving at 68 kilometers per second at its closest approach, fast enough to cross the continental United States in less than 2 minutes. That's hyperfast by solar system standards, and it tells us something extraordinary. This visitor will never return. The mathematics are unforgiving. 3I-ATLAS follows what astronomers call a hyperbolic orbit, meaning it's gravitationally unbound from our solar system. Once it swings around the Sun this October, it will accelerate back into the interstellar void at 58 kilometers per second, never to be seen again. In cosmic terms, we're witnessing a one-night stand between our solar system and a wanderer from elsewhere. But where is elsewhere exactly? Trace 3I-ATLAS's trajectory backward through space and time, and you arrive at a startling conclusion. This comet originated from the direction of Sagittarius, near the galactic center side of our sky. It's been cruising through interstellar space for potentially billions of years, carrying with it the chemical fingerprints of whatever stellar neighborhood birthed it. The age estimates are staggering. Multiple kinematic analyses suggest 3I-ATLAS belongs to what astronomers call the thick disk population of our galaxy, ancient stars and debris with orbital characteristics that scream, "I was here first." Some studies bracket its age between 3 and 11 billion years. Others push that estimate beyond 7.6 billion years, making this comet potentially older than our entire solar system. Let that settle for a moment. The rocky nucleus of 3I-ATLAS, no bigger than a small city, may have formed when our Sun was nothing more than a diffuse cloud of gas and dust. It watched our galaxy evolve through cosmic epochs we can barely imagine. It survived stellar explosions, gravitational perturbations, and the slow churn of galactic dynamics that eventually ejected it from whatever system gave it birth. Think of 3I-ATLAS as a time capsule wrapped in ice and rock, preserving chemical conditions from an era when metallicity was lower and stellar formation followed different rules. The thick disk population represents the galaxy's middle age, a time when star formation was more violent and less organized than the relatively genteel environment that produced our Sun and its planetary retinue. This ancient heritage explains why 3I-ATLAS behaves so differently from our familiar solar system comets. Its carbon dioxide-dominated chemistry reflects formation conditions we don't see in our local neighborhood. The ice compositions, the dust-to-gas ratios, even the way it responds to solar heating, all of these characteristics bear the signature of a different time and place. The journey itself beggars comprehension. For millions or billions of years, 3I-ATLAS drifted through the cold between the stars, its surface perhaps occasionally stirred by cosmic rays or the faint pressure of starlight. It passed through the outer fringes of other stellar systems, witnessed the birth and death of stars, and slowly tumbled through the galaxy's spiral arms like a message in a bottle thrown into an ocean of vacuum. What finally brought it to us? Probably nothing more dramatic than chance. The same gravitational lottery that occasionally sends asteroids on Earth-crossing orbits or flings planets into interstellar space. Our solar system, plowing through space at 230 kilometers per second around the galactic center, simply happened to intersect 3I-ATLAS's trajectory at precisely the right moment in cosmic history. The encounter timeline reads like a precisely choreographed dance. Perihelion on October 29th, at 1.36 astronomical units from the Sun, closer than Mars but not by much. A near miss of Earth at 1.8 astronomical units in December, close enough for excellent observations but far enough to pose zero threat. And perhaps most intriguingly, a series of planetary encounters that will provide multiple opportunities to study how an ancient interstellar wanderer behaves under modern solar system conditions. But here's what should give us pause. 3I-ATLAS represents just one data point in what must be an enormous population of interstellar objects crisscrossing our galaxy. Current models suggest millions or billions of these cosmic refugees are drifting through space right now, invisible and undetected, until they happen to wander close enough to a star system to warm up and announce their presence. We're not just observing a comet. We're glimpsing the debris field of galactic evolution itself, the scattered remains of countless star systems that have lived, died, and ejected their children into the void. 3I-ATLAS is simultaneously a visitor and a messenger, carrying news from stellar neighborhoods so distant and ancient that their very existence challenges our provincial view of cosmic chemistry. The terrifying scale isn't just about size, it's about time and distance, and the sheer improbability of this moment. An object older than our world, moving faster than anything in our experience, has chosen this brief moment in cosmic history to grace us with its presence. When it leaves us behind in 2026, it will carry with it our measurements, our curiosity, and our wonder into the dark between the stars. Part 3. A living, electrified atmosphere. Forget everything you think you know about empty space. The region around 3I-ATLAS isn't empty. It's a bustling factory of plasma physics, electric fields, and magnetic drama playing out on a scale that makes earthly lightning look like static electricity. That half-sun-wide atmosphere we discussed isn't just passive gas expanding into vacuum. It's what physicists call a dusty plasma, a complex soup of electrically charged particles, tiny grains, and magnetic field lines all interacting in ways that would make any laboratory jealous. The moment sunlight and the solar wind hit 3I-ATLAS's coma, they begin transforming neutral gas molecules into ions, creating a vast electrified atmosphere around that tiny nucleus. Picture this. As carbon dioxide molecules sublimate from the comet's surface, they encounter the sun's ultraviolet radiation and become ionized, stripped of electrons, and left with positive electric charges. These newly created ions don't just drift peacefully into space. They couple with the solar wind's magnetic field, getting swept up and accelerated along magnetic field lines that stretch back to the sun itself. This is how comet tails form. Not from rocket exhaust or atmospheric friction, but from the gentle yet inexorable pressure of magnetized plasma flowing from our star. The ion tail of 3I-ATLAS will point directly away from the sun regardless of the comet's direction of motion, like a cosmic weather vane responding to magnetic field lines invisible to our eyes. But here's where 3I-ATLAS gets interesting. Its retrograde orbit carries it at roughly 175 degrees inclination to the ecliptic plane, almost directly opposite to the direction planets normally travel. More importantly, this path will take the comet across something called the heliospheric current sheet, a vast, wavy boundary in the solar wind where magnetic field polarity reverses. Think of the current sheet as the galaxy's largest windsock, a surface that flutters and ripples as the sun rotates every 27 days. When comets cross this boundary, their plasma environments can change dramatically. Magnetic field reversals can kink tails, create disconnection events, or generate entirely new structures in the coma as different magnetic domains interact. The European Space Agency's Rosetta mission gave us our first intimate look at these plasma phenomena around Comet 67P Churyumov-Gerasimenko. Even that relatively quiet comet developed a surprisingly dynamic ionosphere, complete with electric fields accelerating particles and plasma waves propagating through the coma-like ripples on an electrified pond. 3I-ATLAS, with its massive atmosphere and high activity levels, should provide a natural laboratory for studying these effects on a much grander scale. And we're approaching this encounter during solar maximum, when our star's magnetic field is at its most chaotic. Coronal mass ejections, billion-ton blobs of magnetized plasma hurled from the sun's surface, are more frequent and more violent during these periods. When a CME slams into a comet's atmosphere, the results can be spectacular. Compressed comae, restructured tails, and sometimes complete tail disconnections as magnetic field lines reconnect and release enormous amounts of stored energy. The plasma physics gets even more complex when you consider dust. 3I-ATLAS is shedding microscopic particles along with gas, and these tiny grains become electrically charged in the solar wind environment. Charged dust behaves very differently from neutral material. It can be accelerated by electric fields, trapped in magnetic bottles, or organized into complex structures by plasma instabilities. Some of these dust grains are submicron water ice crystals detected in JWST observations. Others are likely rocky debris from the nucleus surface. Each grain becomes a tiny spacecraft, carrying electric charge and responding to the complex electromagnetic environment surrounding the comet. The result is a three-dimensional sculpture of charged particles, constantly shifting and evolving as the comet moves through different regions of the solar wind. We need to be careful about cause and effect here. Comets don't trigger solar flares or coronal mass ejections. They're simply unlucky victims when these events occur, but they do serve as exquisitely sensitive probes of space weather conditions. The way 3I-ATLAS's tail kinks, disconnects, or brightens tells us more about the solar wind's structure than any spacecraft could measure directly. Current sheet crossings are particularly important because they often coincide with high-speed solar wind streams, regions where the solar wind velocity jumps from 400 to 800 kilometers per second. These stream interaction regions create compression waves that propagate outward from the sun, and when they encounter a comet's atmosphere, they can create remarkable displays of plasma physics in action. The electromagnetic drama isn't just academic. Mars orbiters might catch glimpses of 3I-ATLAS during its October 3rd flyby, providing our first direct measurements of how the red planet's thin atmosphere responds to the comet's charged particle environment. These observations could reveal whether large cometary atmospheres can influence planetary magnetospheres at distances previously thought to be safely remote. What we're witnessing around 3I-ATLAS is essentially a natural particle accelerator operating at astronomical scales. Magnetic field lines stretch and snap like rubber bands, releasing energy that accelerates ions to incredible velocities. Electric fields build up and discharge across distances measured in Earth diameters. And all of this electromagnetic fury is centered around a nucleus smaller than most asteroids. The living, breathing plasma atmosphere of 3I-ATLAS represents one of nature's most exotic states of matter, played out against the infinite backdrop of interplanetary space. It's a reminder that the universe is far more electrically active than our earthbound experience suggests, and that even the emptiest regions of space can become theaters for physics, so dramatic it challenges our understanding of what's possible. Part 4. What 3I-ATLAS is and isn't. Let's address the elephant in the solar system. Every time an interstellar object shows up, the internet explodes with speculation about alien probes, technosignatures, and extraterrestrial surveillance missions. So before we dive deeper into 3I-ATLAS's genuine mysteries, let's establish what we're actually dealing with. 3I-ATLAS is the third confirmed interstellar object, and the second interstellar comet, following in the footsteps of the enigmatic 1I Oumuamua and the more conventional 2I Borisov. But unlike Oumuamua, which sparked endless debates about its strange acceleration and cigar-like shape, 3I-ATLAS displays every characteristic we expect from a natural comet. It has a coma, it has gas and dust production. It responds to solar heating exactly as physics predicts. The safety question first. 3I-ATLAS will never come closer than 1.8 astronomical units to Earth, roughly 168 million kilometers. That's more than the distance from Earth to the Sun, placing it firmly in the interesting but harmless category. Mars gets a much closer encounter at 0.19 astronomical units on October 3rd, but even that represents 19 million kilometers of comfortable buffer. So what makes 3I-ATLAS special isn't danger, it's chemistry, scale, and timing. The comet's carbon dioxide-dominated atmosphere represents an extreme we've never seen before in our solar system. Its enormous coma challenges our understanding of how small nuclei can generate such massive gas production. And its arrival during solar maximum provides a once-in-a-lifetime opportunity to study interstellar plasma physics under the most active conditions our Sun can provide. The natural comet signatures are unmistakable across multiple observatories. Hubble sees the classic fuzzy coma structure. JWST detects the spectroscopic fingerprints of sublimating ices. SPHEREX maps the extended carbon dioxide envelope. Ground-based telescopes track the predictable brightening as solar heating increases. Every measurement points to the same conclusion. This is a dirty snowball from another star system, behaving exactly as dirty snowballs should. But let's acknowledge the elephant's cousin. 3I-ATLAS's chemistry is genuinely weird. That 8:1 carbon dioxide to water ratio sits 6.1 standard deviations above typical comet compositions. In statistics, anything beyond 3 sigma is considered highly unusual. 6 sigma events are supposed to happen once in a billion observations. Either 3I-ATLAS represents an incredibly rare statistical fluke, or its formation environment was radically different from anything we see in our local stellar neighborhood. The scientific method demands we pursue the most exotic hypotheses only after exhausting conventional explanations. And there are plenty of conventional ways to create a carbon dioxide-rich comet. Formation beyond the carbon dioxide frost line, where temperatures are cold enough to freeze CO2 directly from gas. Heavy irradiation from a massive star during the comet's youth. An insulating crust that preferentially releases carbon dioxide while trapping water vapor beneath. Each explanation carries implications for understanding planet formation around other stars. If 3I-ATLAS formed in the outer regions of its birth system, it tells us something about the structure and chemistry of alien protoplanetary disks. If it experienced heavy stellar irradiation, it constrains the type of star that could produce such chemistry. If crustal evolution is responsible, it reveals how billion-year journeys through interstellar space might alter comet surfaces. The nucleus itself remains frustratingly elusive. Hubble's upper limit of 5.6 kilometers in diameter could hide a nucleus as small as 0.3 of a kilometer across. That uncertainty spans 2 orders of magnitude in mass, making it impossible to calculate precise gas production rates or predict future behavior with confidence. We're essentially studying a comet by its shadow, inferring the properties of an invisible core from the atmosphere it creates. Some early size estimates suggested much larger nuclei, perhaps 46 kilometers across based on near-infrared flux measurements. But these calculations depend heavily on assumptions about surface reflectivity and dust-to-gas ratios that may not apply to interstellar objects. The Hubble imaging constraint remains our most reliable measurement because it doesn't depend on assumptions about albedo or composition. Public interest in interstellar objects creates a challenging environment for scientific communication. Every observation gets scrutinized for signs of artificial origin. Every unusual measurement spawns speculation about extraterrestrial technology. The scientific community has learned to present findings with extra caution, clearly separating established facts from preliminary interpretations. This caution serves everyone well. Extraordinary claims about technosignatures require extraordinary evidence, and that evidence simply doesn't exist for 3I-ATLAS. The comet's behavior falls comfortably within the range of natural phenomena, even if it represents an extreme example of those phenomena. But natural doesn't mean boring. 3I-ATLAS offers us a direct sample of interstellar chemistry, a billion-year-old time capsule from the galaxy's thick disk population. It's carrying information about star formation conditions that predate our solar system's existence. It's demonstrating plasma physics on scales we can't reproduce in any laboratory. It's providing our first opportunity to study how ancient alien ices respond to modern solar heating. The real mystery isn't whether 3I-ATLAS is artificial, it's how nature managed to create something so extreme that it challenges our understanding of what's possible. Sometimes the most profound discoveries come not from finding what we never expected, but from finding familiar phenomena pushed to such extremes that they force us to revise our basic assumptions about how the universe works. 3I-ATLAS is a natural comet. But it's a natural comet operating at the very edges of what nature apparently allows, and that might be even more interesting than any artifact could ever be. Part 5. The Interstellar Proof. July 1st, 2025. The ATLAS Survey Telescope at Rio Hurtado, Chile, captures something unusual in the constellation Sagittarius. Just another faint smudge against the star-crowded background of our galaxy's central regions. The initial designation reads like cosmic alphabet soup, A11PL3Z. Nothing in that string of characters hints at the extraordinary nature of what ATLAS has just found. 24 hours later, everything changes. The Minor Planet Center issues Circular MPEC 2025-N12, and suddenly that anonymous smudge has a name and a destiny. C/2025-N1 becomes 3I-ATLAS, the third confirmed interstellar object in human history. The I designation isn't awarded lightly. It means NASA's orbital dynamicists have calculated a hyperbolic trajectory that places this object's origin firmly outside our solar system. The mathematics are brutal and beautiful. Orbital eccentricity of 1.047, meaning the trajectory curves away from the Sun in a perfect hyperbola. Velocity at infinity of 58 kilometers per second, fast enough to escape the Sun's gravitational influence entirely. These numbers don't lie, and they don't leave room for interpretation. 3I-ATLAS is a visitor, not a resident, but July's discovery represents just the end of the beginning. Astronomers immediately begin scanning archival images, searching for earlier sightings that could extend the observational arc and refine the orbital solution. These recoveries are like forensic evidence, allowing scientists to trace the comet's path through space with increasing precision. Each additional observation point tightens the mathematical constraints on 3I-ATLAS's origin and destination. The announcement ripples through astronomical networks with remarkable speed. NASA's Planetary Defense Coordination Office issues a public statement confirming the interstellar nature and emphasizing the safe flyby distance. At 670 million kilometers from Earth at the time of discovery, 3I-ATLAS poses no threat to our planet, but it offers unprecedented scientific opportunities. Educational outreach kicks into high gear almost immediately. Astronomy websites rush to explain the difference between interstellar and dangerous, helping the public understand that exotic origin doesn't equal existential threat. The messaging is crucial because interstellar objects tend to trigger both fascination and fear in equal measure. First images from ground-based telescopes reveal the challenges ahead. 3I-ATLAS appears as a faint, fuzzy star against the dense background of the Milky Way's central regions. Tracking the comet's motion requires exposures that streak the surrounding stars, creating images that look more like cosmic abstract art than scientific data. The Virtual Telescope Project and other amateur networks begin their own observation campaigns, contributing to the global effort to characterize this visitor. Hubble Space Telescope soon enters the game, its sharp vision cutting through atmospheric turbulence to place the first meaningful constraints on the nucleus size. The result, no larger than 5.6 kilometers across, establishes 3I-ATLAS as a relatively small but extraordinarily active comet. The ratio of coma size to nucleus diameter exceeds anything seen in our solar system's comet population. Meanwhile, JWST begins preparing its own observation campaign. The world's most powerful space telescope will bring unprecedented spectroscopic capabilities to bear on 3I-ATLAS, promising detailed chemical analysis of the coma composition. These observations will provide our first direct measurements of interstellar ice chemistry, revealing whether alien comets follow the same formation rules as our local population. The discovery timeline illustrates how modern astronomy operates as a global network. ATLAS detects, the Minor Planet Center processes and distributes, major observatories plan follow-up campaigns, and amateur astronomers worldwide contribute additional observations. Within weeks of discovery, 3I-ATLAS becomes one of the most closely watched objects in the solar system, but the orbital solution continues evolving as new observations arrive. Each measurement slightly adjusts the calculated trajectory, refining our understanding of where 3I-ATLAS came from and where it's going. The hyperbolic nature of the orbit never changes. That fundamental conclusion emerged clearly from the first few nights of observations. But the precise orbital parameters keep shifting as systematic errors are identified and corrected. This process highlights a crucial aspect of astronomical discovery. Initial measurements are always preliminary, and responsible science communication must acknowledge uncertainty while still conveying excitement about new findings. 3I-ATLAS's interstellar origin was certain within days of discovery, but details like the exact perihelion date and closest approach distances required weeks or months to nail down precisely. Archive searches extend the observational record back into May and June, before ATLAS made its official detection. These precovery observations are crucial for determining 3I-ATLAS's exact trajectory and timing. They also reveal that the comet was already developing a measurable coma months before discovery, consistent with carbon dioxide sublimation beginning at large distances from the Sunday. The confirmation process follows strict international protocols developed over decades of asteroid and comet discoveries. The Minor Planet Center collects observations from multiple sites, calculates preliminary orbits, and issues circulars only when the trajectory is certain. For interstellar objects, additional scrutiny ensures that measurement errors or systematic biases don't lead to false claims of extrasolar origin. 3I-ATLAS passed every test. Its hyperbolic orbit appears in calculation after calculation, refined and confirmed by observations from dozens of telescopes worldwide. The velocity measurements align with theoretical predictions for the interstellar object population. The trajectory traces back to a plausible region of our galaxy's thick disk, consistent with kinematic models of stellar populations. By the end of July, 3I-ATLAS has transformed from anonymous sky survey detection to confirmed interstellar visitor. The discovery represents just the first step in what promises to be an 18-month observation campaign spanning from now through the comet's departure in late 2026. We've identified our target. Now the real science begins. Part 6. Chemistry at Terrifying Scale. When JWST turned its near-infrared spectrograph toward 3I-ATLAS, it revealed something that should make every planetary scientist pause and reconsider what they thought they knew about comet chemistry. The numbers are stark, unprecedented, and frankly a little unsettling. Carbon dioxide to water ratio of 8:1, 6.1 standard deviations above the normal range for solar system comets. Let that sink in. In statistics, 3 sigma events are rare, 4 sigma events are extraordinary, 6 sigma events are supposed to happen roughly once per billion observations. Either we've witnessed an astronomical lottery ticket, or 3I-ATLAS represents chemistry so exotic that it demands a complete revision of our understanding of comet formation. The JWST observations paint a detailed picture of alien ice composition. Carbon dioxide dominates at 4.3 micrometers. Carbon monoxide appears at 4.7 micrometers. Water vapor shows up at 2.7 micrometers, but as a distinctly minor component. And scattered throughout the spectrum, the signatures of fine water ice grains less than 1 micrometer across, suspended in a coma dominated by carbon-bearing volatiles. Spherex independently confirms this chemical weirdness, mapping the extended carbon dioxide envelope across its 696,000 kilometer diameter. The convergence of results from 2 completely different observational approaches eliminates any possibility of instrumental error or calibration problems. 3I-ATLAS really is that carbon dioxide rich. But why? The leading hypotheses read like a menu of exotic formation scenarios. Perhaps 3I-ATLAS formed beyond the carbon dioxide frost line in its birth system, where temperatures dropped low enough for CO2s to condense directly from gas into solid ice. This would require formation at distances where most protoplanetary disks are thought to be too sparse to build comet-sized objects. Alternatively, heavy stellar irradiation during the comet's youth might have preferentially removed water while leaving carbon dioxide trapped in protective ice matrices. This scenario demands a formation environment near a massive luminous star, the kind of stellar neighborhood that would subject forming planetesimals to radiation fields thousands of times more intense than anything our sun could provide. The third possibility is more subtle but equally significant: surface evolution during 3I-ATLAS's billion-year journey through interstellar space. Cosmic ray bombardment, micrometeorite impacts, and the gentle but persistent pressure of interstellar radiation could have created an insulating crust that preferentially releases carbon dioxide while trapping water vapor beneath the surface. Each explanation carries profound implications for our understanding of planet formation across the galaxy. If 3I-ATLAS formed in the outer regions of an alien protoplanetary disk, it constrains the mass distribution and temperature structure of planetary systems around different types of stars. If stellar irradiation is responsible, it tells us about the violent environments where some planetary systems take shape. If crustal evolution during interstellar transit is the key, it reveals how billion-year journeys through the void might alter the surfaces of small bodies. The production rates derived from JWST spectroscopy are staggering when scaled to human comprehension. Conservative estimates suggest 3I-ATLAS is currently losing several tons of material per second, with carbon dioxide accounting for the vast majority of that mass loss. Picture a freight train's worth of ice sublimating into space every minute, expanding the coma at velocities approaching 1 kilometer per second. But here's what makes 3I-ATLAS even more unusual. This extreme gas production is happening at 3 astronomical units from the Sun, where solar system comets typically show minimal activity. Most of our familiar periodic comets don't begin serious outgassing until they approach 2 astronomical units or closer. 3I-ATLAS is already operating at peak efficiency, while still farther from the Sun than Mars. The spectroscopic signatures also reveal OCS, carbonyl sulfide, a molecule that requires specific formation conditions and tells us about the sulfur chemistry in 3I-ATLAS's birth environment. The detection suggests complex carbon-sulfur-oxygen chemistry during the comet's formation, possibly indicating sulfur-rich ice condensation in a protoplanetary disk with different elemental abundances than our solar system. Comparing 3I-ATLAS with 2I-Borisov, the previous interstellar comet, reveals the chemical diversity of alien planetary systems. Borisov showed unusually high carbon monoxide abundances but maintained more typical carbon dioxide levels. 3I-ATLAS pushes the carbon dioxide abundance into completely uncharted territory, while showing more moderate carbon monoxide enhancement. Each interstellar comet samples different formation conditions, different stellar environments, different epochs of galactic chemical evolution. The JWST observations are scheduled to continue post-perihelion, allowing astronomers to monitor how 3I-ATLAS's chemistry evolves as solar heating increases and then decreases during its solar system flyby. These follow-up measurements will reveal whether the carbon dioxide dominance represents intrinsic nucleus composition or results from preferential release due to surface effects. Media coverage of the chemical results has been generally accurate but occasionally sensationalized. Headlines about alien chemistry and impossible ratios capture public attention while sometimes obscuring the careful scientific work required to extract composition information from spectroscopic data. The peer review process for JWST results ensures that published findings meet rigorous standards, but preprint servers allow preliminary results to circulate before formal publication. What's particularly striking about 3I-ATLAS's chemistry is how it simultaneously confirms and challenges our understanding of comet formation. The basic physics of ice sublimation works exactly as expected. Carbon dioxide sublimates at lower temperatures than water, explaining why the comet became active so far from the Sunday, but the extreme abundance ratios pushed this familiar physics into completely unexplored parameter space. The chemical fingerprint of 3I-ATLAS reads like a message from an alien world, encoded in molecular vibrations and preserved in ice for billions of years. Each spectral line carries information about temperatures, pressures, and elemental abundances in a stellar system so distant that its very existence was unknown until 3I-ATLAS arrived to tell us about it. We're not just studying a comet, we're conducting archaeology on a galactic scale, using chemistry to reconstruct the conditions that prevailed when our galaxy was younger and star formation followed different rules. Part 7. How big is the nucleus? What we know versus debate. The nucleus of 3I-ATLAS presents us with one of the most frustrating mysteries in modern astronomy, an object simultaneously too small to see clearly and too active to ignore. Hubble Space Telescope, humanity's sharpest eye in space, can only tell us that the solid core measures no more than 5.6 kilometers across. It could be as small as 0.3 of a kilometer in diameter. That's an uncertainty spanning 2 orders of magnitude in mass. NASA's official summary maintains that conservative upper limit, 5.6 kilometers maximum diameter. This number emerges from careful point spread function modeling, where astronomers attempt to subtract the bright, fuzzy coma from Hubble images to reveal the underlying nucleus. The process is like trying to photograph a birthday candle flame while subtracting the glow, technically possible but fraught with systematic uncertainties. The challenge stems from 3I-ATLAS's extraordinary activity level. Most comets at 3 astronomical units from the Sun show minimal coma development, making nucleus detection relatively straightforward. But 3I-ATLAS is already surrounded by that massive carbon dioxide envelope, creating a bright background that completely overwhelms the much fainter light reflected by the solid nucleus itself. Early estimates suggested dramatically different sizes. Some analyses based on near-infrared flux measurements propose nuclei as large as 46 kilometers across. These calculations attempted to work backward from total brightness to nucleus size, making assumptions about albedo, surface reflectivity, and dust production rates that may not apply to interstellar objects with alien chemistry and billion-year surface evolution. The controversy highlights a fundamental problem in comet science. Nucleus size determination depends heavily on assumptions about surface properties that we can't measure directly. A dark nucleus reflects less sunlight per unit area, requiring a larger diameter to produce observed brightness levels. A bright nucleus achieves the same brightness with a smaller diameter. Without independent constraints on surface reflectivity, size calculations become exercises in educated guesswork. Hubble's imaging constraint sidesteps most of these assumptions by directly attempting to detect the nucleus as a point source against the coma background. The 5.6 kilometer upper limit emerges from the telescope's resolution limits and the brightness ratio between nucleus and surrounding gas. If 3I-ATLAS's nucleus were larger than this limit, Hubble should have detected it as a resolved or partially resolved object, but even Hubble's measurement carries significant uncertainties. The point spread function modeling requires precise knowledge of how the telescope's optics spreads starlight, and small errors in this calibration can propagate into large errors in nucleus size limits. Additionally, if the nucleus has an extremely dark surface, darker than typical asteroids or comet nuclei, it might remain undetected even if it's larger than 5.6 kilometers. The size uncertainty cascades into every other aspect of 3I-ATLAS science. Gas production rates, surface composition models, and activity predictions all depend on knowing the nucleus surface area available for ice sublimation. A 3-kilometer nucleus has roughly 100 times less surface area than a 30-kilometer nucleus, implying dramatically different sublimation physics to achieve the same observed gas production. This uncertainty reveals something profound about the nature of cometary activity. We tend to think of comets as simple dirty snowballs where larger objects naturally produce more gas and dust. But 3I-ATLAS demonstrates that the relationship between nucleus size and activity level can be far more complex. A small but highly active nucleus might indicate unusual ice composition, efficient heat transfer, or surface structures that maximize sublimation area through fractures and cavities. The size debate also illustrates how different measurement techniques can yield conflicting results when pushed to their limits. Photometric methods that analyze total brightness work well for typical comets with well-understood properties. Direct imaging methods excel when the nucleus is large enough and sufficiently separated from its coma. But 3I-ATLAS occupies an uncomfortable middle ground where neither technique provides definitive answers. Perhaps most frustratingly, the size uncertainty affects our ability to predict 3I-ATLAS's future behavior. Will the gas production continue increasing as the comet approaches perihelion? Will the coma grow even larger, or will depletion effects begin limiting activity? The answers depend critically on how much ice remains in the nucleus and how efficiently it can sublime under increased solar heating. Comparative analysis with other comet nuclei provides some context for interpreting the size constraints. Halley's Comet, probably the most famous periodic comet, measures about 11 kilometers across and produces spectacular displays when active. If 3I-ATLAS really is only 3 to 5 kilometers in diameter, its current activity level suggests either much more efficient ice sublimation or radically different surface properties than anything we see in solar system comets. The albedo assumption problem exemplifies a broader challenge in astronomy, inferring physical properties from limited observational data. We can measure how much light 3I-ATLAS reflects, but translating that measurement into size requires assumptions about surface composition, roughness, and age. Interstellar objects with billion-year exposure to cosmic radiation might develop surface properties unlike anything in our local comet population. Recent advances in thermal modeling offer potential solutions to the size uncertainty. By observing 3I-ATLAS at multiple infrared wavelengths, Astronomers can potentially separate thermal emission from reflected sunlight, providing independent constraints on nucleus size that don't depend on albedo assumptions. These techniques work best for objects with measurable thermal emission, requiring observations as 3I-ATLAS approaches closer to the Sunday. The media coverage of 3I-ATLAS's size has sometimes conflated different types of measurements, reporting coma diameters and nucleus estimates as if they were comparable quantities. Science communication faces the challenge of explaining why astronomers can measure a 696,000-kilometer atmosphere but remain uncertain about a 5-kilometer nucleus. The answer lies in the fundamental difference between extended, bright objects and compact, faint ones. Ground-based telescopes continue monitoring 3I-ATLAS as it approaches perihelion, searching for any changes in brightness or morphology that might provide additional clues about nucleus properties. Amateur astronomers with modest equipment can contribute to these observations, demonstrating how citizen science complements professional research programs. What emerges from this size uncertainty is a reminder that astronomy often proceeds through gradual refinement rather than definitive breakthroughs. The 5.6-kilometer upper limit represents our best current constraint on 3I-ATLAS's nucleus, but it's certainly not our final answer. As the comet's geometry changes and new observations accumulate, that uncertainty range should gradually narrow. The nucleus size mystery also highlights the unique scientific value of interstellar objects. Every measurement we make of 3I-ATLAS must be interpreted without the benefit of decades of previous observations or detailed knowledge of formation conditions. We're essentially learning comet physics from scratch, using an object whose properties may differ fundamentally from everything in our experience. When 3I-ATLAS completes its solar system flyby and heads back into interstellar space, it will carry with it whatever secrets its nucleus size holds. Our window for resolving this mystery spans just 18 months, from discovery to departure. The clock is ticking, the telescopes are watching, and somewhere in that blazing coma lies a nucleus whose true dimensions will determine how we understand this most extraordinary visitor. Part 8. Two Faces of Size. Optical versus infrared. The tale of 3I-ATLAS is really a story about seeing the invisible, measuring the unmeasurable, and discovering that size is a far more slippery concept than most people realize. When we ask how big this comet really is, the answer depends entirely on what kind of light you're using to look at it. Invisible light, the same wavelengths our eyes evolved to detect. 3I-ATLAS appears as a fuzzy star roughly 26,400 kilometers across. That's about 2 Earth diameters, impressive by terrestrial standards but fairly typical for an active comet at moderate solar distances. Ground-based telescopes like the Gran Telescopio Canarias capture this optical coma as a compact, relatively dense cloud of dust and gas illuminated by reflected sunlight. But switch to near-infrared wavelengths, and 3I-ATLAS transforms into something utterly different. Spherics and JWST reveal a gossamer envelope of carbon dioxide stretching at least 348,000 kilometers in every direction, 696,000 kilometers across, roughly half the diameter of our Sunday. Same comet, same moment in time, but an entirely different definition of size. This isn't measurement error or instrumental bias, it's physics. Different molecules emit and absorb light at different wavelengths, making them visible or invisible depending on which part of the electromagnetic spectrum you examine. The optical coma traces dust particles and certain gas species that interact strongly with visible light. The infrared envelope reveals carbon dioxide molecules that glow brightly in thermal infrared but remain nearly transparent to our eyes. Think of it like looking at a jellyfish underwater. In bright light, you see the dense bell and trailing tentacles, compact, clearly defined, easy to measure. but switch to ultraviolet, and suddenly the entire creature lights up with bioluminescence extending far beyond its visible boundaries. Same organism, different revelation of its true extent. The nested structure of 3I-ATLAS's atmosphere creates a cosmic Russian doll. At the center lies that elusive nucleus, no more than 5.6 kilometers across. Surrounding it, a dense inner coma of dust and mixed gases extends roughly 13,000 kilometers in radius, visible to optical telescopes as a fuzzy star-like object. Beyond that, a much more tenuous but vastly larger envelope of carbon dioxide stretches hundreds of thousands of kilometers into space, detectable only in specific infrared wavelengths. Each layer tells a different part of the comet's story. The inner optical coma reveals how dust and gas interact in the immediate vicinity of the nucleus, where sublimation rates are highest and particle densities remain substantial. This region undergoes rapid evolution as solar heating changes, developing the jets, spirals, and asymmetries that make comet photography so compelling. The outer carbon dioxide envelope operates on much larger scales and longer timescales. Gas molecules in this region have been traveling outward from the nucleus for days or weeks, expanding and cooling as they move through the vacuum of space. Their low density makes them invisible to optical telescopes, but bright in infrared wavelengths where carbon dioxide's molecular vibrations produce characteristic emission lines. JWST's spectroscopic observations reveal additional complexity within this infrared envelope. Water ice grains less than 1 micrometer across scatter short wavelength infrared light, creating a third component to 3I-ATLAS's multi-layered atmosphere. These tiny crystals probably condense from water vapor in the cold outer regions of the coma, forming a population of particles too small to see individually but detectable through their collective scattering properties. The wavelength-dependent size measurements create communication challenges for astronomy educators and journalists. Headlines proclaiming 3I-ATLAS as half the sun's width are technically accurate, but potentially misleading if readers assume this refers to the solid comet itself. The distinction between nucleus, coma, and extended atmosphere requires careful explanation to avoid confusion. This measurement complexity reflects a broader truth about astronomical objects. They rarely have single, well-defined sizes. Galaxies appear different in optical light versus radio waves. Stars have photospheres, chromospheres, and coronas extending to vastly different distances. Planets have solid surfaces, atmospheres, and magnetospheres that define multiple boundaries depending on what physical process you're measuring. 3I-ATLAS pushes this concept to an extreme. The ratio between its nuclear diameter and its carbon dioxide envelope spans 5 orders of magnitude, roughly the same as comparing a marble to the state of Texas. No other object in our solar system demonstrates such a dramatic range of characteristic scales within a single system. The evolution of these nested structures provides crucial information about 3I-ATLAS's internal composition and thermal properties. As the comet approaches perihelion, increased solar heating should expand both the optical and infrared components, but potentially at different rates if the nucleus composition is layered or heterogeneous. Ground-based observatories face particular challenges when imaging 3I-ATLAS across multiple wavelengths. The comet's trajectory carries it through the most star-crowded regions of our sky, requiring careful background subtraction and image processing to separate the comet's various atmospheric components from foreground and background stars. The size dichotomy also affects how we understand 3I-ATLAS's interaction with the solar wind. The optical coma defines the dense plasma environment where most ion-neutral collisions occur, but the extended carbon dioxide envelope determines the overall cross-sectional area for solar wind interaction, influencing tail formation and space weather effects across a much larger volume. Amateur astronomers can contribute to monitoring both size, scales, with modest telescopes capable of tracking changes in the optical coma, while larger instruments equipped with appropriate filters might detect portions of the extended infrared envelope. The citizen science potential of 3I-ATLAS spans multiple observational techniques and wavelength ranges. What emerges from this tale of two sizes is a lesson about the importance of multi-wavelength astronomy. Each part of the electromagnetic spectrum reveals different physical processes, different spatial scales, and different time evolution patterns. 3I-ATLAS isn't uniquely large or uniquely small, it's uniquely complex, with characteristic dimensions spanning 5 orders of magnitude depending on what you're measuring and how you're measuring it. Part 9. The geometry that magnifies effects. Orbital mechanics can be surprisingly personal. The precise trajectory of 3I-ATLAS through our solar system reads like a cosmic itinerary designed to maximize both scientific opportunity and dramatic potential. This isn't random wandering, it's a carefully choreographed dance between gravity and velocity that will showcase interstellar comet physics under the most revealing conditions possible. The numbers tell the story. Orbital inclination of 175 degrees means 3I-ATLAS is moving retrograde, traveling in the opposite direction from planetary motion. More importantly, it's nearly coplanar with the ecliptic, tilted only 5 degrees from the plane where planets orbit. This combination creates the worst possible traffic pattern, a cosmic head on collision course with the entire architecture of our solar system. The encounter sequence reads like a planetary tour gone wrong. Mars at 0.19 astronomical units on October 3rd, close enough that the red planet's gravity will measurably deflect the comet's trajectory. Perihelion at 1.36 astronomical units on October 29th, placing 3I-ATLAS between Earth and Mars at its closest approach to the Sunday. Venus at 0.65 astronomical units on November 3rd. Earth at 1.8 astronomical units on December 19th. Jupiter at 0.36 astronomical units on March 16th, 2026. Each encounter represents more than just a close flyby. These are opportunities for gravitational physics, plasma interaction studies, and multi-point observations that occur perhaps once per century for any given comet. The retrograde geometry means 3I-ATLAS will be moving at maximum relative velocity during each planetary encounter, compressing observation windows but maximizing the drama of gravitational interactions. The near-ecliptic trajectory carries profound implications for 3I-ATLAS's interaction with solar wind structures. The ecliptic plane isn't just where planets orbit, it's also where the solar wind's most complex dynamics play out. The heliospheric current sheet, that vast boundary where the sun's magnetic field changes polarity, oscillates around the ecliptic with a period of 27 days as our star rotates. Most comets spend relatively little time near the current sheet because their orbits are either highly inclined or highly elliptical. 3I-ATLAS will cruise along this magnetic boundary for months, repeatedly crossing between regions of opposite magnetic polarity. Each crossing represents a potential trigger for tail disconnection events, plasma instabilities, and the kind of space weather phenomena that make comet photography spectacular. The geometry also explains why 3I-ATLAS will be so difficult to observe from Earth around perihelion. Solar conjunction occurs when the comet passes nearly behind the Sun from our perspective, making ground-based observations impossible during the period of maximum activity. This is astronomy's equivalent of Murphy's Law. The most interesting events often occur when we're least able to observe them. But the retrograde trajectory that complicates Earth-based observations creates unique opportunities elsewhere. Mars orbiters will have an excellent view during the October 3rd flyby, when 3I-ATLAS reaches magnitude 11 as seen from the red planet. That's bright enough for detailed imaging and spectroscopy, potentially providing our first spacecraft observations of an active interstellar comet. The speed implications are staggering. At perihelion, 3I-ATLAS will be moving 68 kilometers per second relative to the Sun, fast enough to cross the continental United States in 90 seconds. Coordinated observation campaigns must account for this velocity when planning telescope pointings and exposure sequences. Miss your timing window by a few hours, and the comet will have moved significantly against the background stars. Jupiter's encounter in March 2026 offers perhaps the most scientifically valuable opportunity. By then, 3I-ATLAS will be far from perihelion and moving through a very different solar wind environment. High-speed streams and correlating interaction regions dominate the outer solar system's space weather, creating conditions that might trigger different types of plasma phenomena than the coronal mass ejection-dominated inner system. The orbital geometry also affects how 3I-ATLAS's dust and ion tails develop and evolve. Dust tails point away from the Sun due to radiation pressure, while ion tails align with magnetic field lines in the solar wind. The retrograde motion means these tails will sometimes point in dramatically different directions, creating the distinctive forked appearance that makes comets photogenic. Navigation and tracking present unique challenges for such a fast-moving target. Ground-based telescopes must continuously update their pointing to follow 3I-ATLAS against the stellar background, often resulting in streaked star images that complicate photometric measurements. Space-based observatories like Hubble and JWST face similar tracking difficulties, requiring special observation modes designed for moving targets. The near-ecliptic geometry maximizes 3I-ATLAS's time within what space physicists call the interaction region, the volume of space where planetary magnetospheres, the solar wind, and interplanetary magnetic fields create the most complex plasma dynamics. Most comets spend only brief periods in this region, but 3I-ATLAS will cruise through it for more than a year. Amateur astronomers face their own geometric challenges. The comet's path through crowded Milky Way star fields makes identification difficult even with detailed finder charts. The retrograde motion means 3I-ATLAS appears to move backward relative to most celestial objects, potentially confusing observers accustomed to typical planetary and asteroidal motions. Spacecraft mission planners have studied the possibility of redirecting existing interplanetary probes to intercept 3I-ATLAS, but the geometric constraints prove nearly impossible to overcome. The high relative velocities and retrograde trajectory would require enormous fuel expenditures to achieve even brief encounters, placing such missions beyond current technological capabilities. What emerges from this geometric analysis is an appreciation for how orbital mechanics amplifies scientific opportunity. 3I-ATLAS's trajectory isn't just a path through space, it's a prescription for maximum interaction with every component of our solar system's complex electromagnetic environment. The same geometry that makes observations challenging also makes them uniquely valuable, providing data that might not be obtainable for centuries. Part 10. The Observing Armada. When an interstellar visitor arrives in our cosmic neighborhood, humanity responds with everything we've got. The observational campaign targeting 3I-ATLAS represents the largest coordinated study of a single comet in astronomical history, marshalling ground-based telescopes, space observatories, and citizen scientists into a unified effort to extract every possible piece of information before this ancient wanderer disappears forever. JWST leads the charge with its near-infrared spectrograph, dissecting 3I-ATLAS's coma across multiple wavelengths that reveal different chemical components. At 1.2 micrometers, the telescope maps dust distribution and scattering properties. At 2.7 micrometers, water vapor emissions paint a picture of H2O production rates and spatial distribution. The 4.3 micrometer band traces carbon dioxide, 3I-ATLAS's dominant volatile component, while 4.7 micrometers reveals carbon monoxide signatures that constrain formation temperature and irradiation history. These JWST observations represent far more than pretty pictures. Each wavelength band corresponds to specific molecular vibrations and electronic transitions that encode information about temperature, density, velocity, and composition throughout 3I-ATLAS's enormous atmosphere. The spectroscopic data allows astronomers to construct three-dimensional maps of chemical abundance, essentially performing a dissection of interstellar ice chemistry on scales impossible to achieve in any laboratory. Spherix complements JWST's detailed point observations with wide-field mapping that captures 3I-ATLAS's full extent in near-infrared wavelengths. This space-based survey telescope traced the carbon dioxide envelope to its current limit of 348,000 kilometers radius, revealing that the detectable atmosphere extends far beyond even optimistic theoretical predictions. Spherix also identified water ice absorption signatures, indicating that solid particles throughout the coma continue condensing and sublimating as they expand outward from the nucleus. Hubble Space Telescope brings its legendary sharp vision to bear on 3I-ATLAS's innermost regions, attempting to resolve nuclear structure and constrain the solid body's size through careful point spread function modeling. These observations push Hubble's capabilities to their limits, requiring sophisticated image processing techniques to separate the faint nucleus signal from the much brighter surrounding coma. The resulting 5.6 kilometer upper limit on nucleus diameter represents one of the most challenging small object measurements Hubble has ever attempted. Ground-based observatories face unique challenges when targeting 3I-ATLAS. The comet's trajectory carries it through the densest star fields visible from Earth, requiring careful background subtraction and field identification. Gemini North's 8-meter mirror provides the light-gathering power necessary to conduct detailed spectroscopy despite these crowded conditions, monitoring how 3I-ATLAS's composition and activity levels evolve as solar heating increases. The amateur astronomy community has embraced 3I-ATLAS with enthusiasm typically reserved for bright periodic comets. The Virtual Telescope Project and similar citizen science networks provide crucial cadence observations, tracking morphological changes and brightness variations that complement professional observatory campaigns. These amateur contributions prove especially valuable for monitoring rapid changes that might occur between scheduled professional observations. Coordination between observatories requires unprecedented precision. 3I-ATLAS's high velocity means that observation timing must be synchronized to within hours to ensure that different telescopes are studying the same physical phenomena. Target of opportunity scheduling allows observatories to respond quickly to unexpected changes in comet behavior, but coordinating such responses across multiple time zones and institutions presents logistical challenges that test the limits of modern astronomical collaboration. The multi-wavelength approach reveals different aspects of 3I-ATLAS's complex environment. Ultraviolet observations planned for Hubble will probe atomic emissions from the innermost coma, where gas densities remain high enough for collision-induced fluorescence. Optical wavelengths trace dust scattering and certain molecular emissions. Near-infrared reveals thermal emission from warm dust and vibrational transitions from major gas species. Radio observations might detect exotic molecules present in trace abundances. Data processing and analysis present their own challenges. Each observatory uses different instruments, calibration procedures, and data formats, requiring careful cross-calibration to ensure that measurements from different facilities can be meaningfully compared. The International Astronomical Union coordinates standards for comet observation reporting, but 3I-ATLAS's unusual properties sometimes push beyond established conventions. NASA's Planetary Defense Coordination Office serves as a central clearinghouse for 3I-ATLAS observations, collecting and disseminating updates from participating observatories. This coordination proves essential for maintaining public confidence in scientific conclusions, ensuring that preliminary results undergo appropriate peer review before reaching news media, and avoiding the kind of sensationalized reporting that sometimes accompanies unusual astronomical discoveries. The observational armada's scope extends beyond traditional astronomical facilities. Mars orbiters, including the European Space Agency's Mars Express and NASA's MAVEN, might attempt observations during 3I-ATLAS's October 3rd flyby, potentially providing our first direct spacecraft measurements of an interstellar comet's plasma environment. These observations would complement remote sensing data with in-situ particle and field measurements impossible to obtain from Earth-based telescopes. Communication of results requires careful attention to uncertainty and preliminary versus final conclusions. Astronomical observations typically undergo months or years of analysis before reaching peer-reviewed publication, but public interest in 3I-ATLAS creates pressure for rapid result dissemination. Preprint servers allow researchers to share preliminary findings while clearly marking them as preliminary, but news media sometimes report these early results as definitive conclusions. The citizen science component extends beyond amateur telescope observations to include computational contributions. Projects like distributed computing networks can assist with data processing and analysis, while online collaboration platforms allow amateur astronomers to contribute to morphology monitoring and brightening predictions. These contributions demonstrate how modern astronomy increasingly relies on community participation across multiple levels of expertise. What emerges from this coordinated observational campaign is a new model for studying rare astronomical phenomena. Rather than relying on serendipitous observations by individual research groups, 3I-ATLAS has prompted the astronomical community to develop systematic, collaborative approaches that maximize scientific return from fleeting opportunities. This template will prove invaluable when future interstellar objects arrive, ensuring that humanity is ready to extract maximum scientific value from each cosmic visitor. The observational armada targeting 3I-ATLAS represents more than just telescope time and data collection. It's a demonstration of how modern astronomy operates as a global enterprise, combining cutting-edge technology with international cooperation and citizen participation to answer fundamental questions about our place in the galaxy. Part 11. Space Weather. What to expect. Solar maximum has arrived, and 3I-ATLAS couldn't have picked a better time to visit. Our Sun is approaching peak activity in its 11-year magnetic cycle, spawning coronal mass ejections, high-speed wind streams, and the kind of chaotic magnetic field conditions that transform comet tails from gentle streamers into spectacular displays of celestial violence. But let's be absolutely clear about cause and effect. 3I-ATLAS didn't trigger solar maximum, and solar maximum isn't responding to 3I-ATLAS. The Sun operates on its own magnetic schedule, completely indifferent to whatever visitors happen to be passing through the inner solar system. What we're witnessing is pure cosmic coincidence, an ancient interstellar wanderer arriving just as our star enters its most temperamental phase. The timing creates unprecedented opportunities for studying comet plasma physics under extreme conditions. Coronal mass ejections, billion-ton blobs of magnetized plasma hurled from the Sun at speeds up to 2,000 kilometers per second, occur several times per week during solar maximum. When one of these magnetic monsters slams into 3I-ATLAS's extended atmosphere, the results should be spectacular: compressed comae, restructured tails, and possibly complete tail disconnection events, as magnetic field lines snap and reconnect with explosive force. Historical precedents exist for such space weather interactions. Comet McNaught in 2007 experienced dramatic tail disconnections during a period of moderate solar activity, creating images that looked more like cosmic lightning bolts than the gentle streamers typically associated with comet tails. 3I-ATLAS, with its massive atmosphere and proximity to solar maximum conditions, could produce even more dramatic displays. The physics underlying these interactions reads like a textbook on plasma instabilities. When a coronal mass ejection's magnetic field encounters 3I-ATLAS's ionized coma, the two magnetic environments don't merge smoothly. Instead, they undergo magnetic reconnection, a process where opposing field lines break and reform, releasing enormous amounts of stored magnetic energy in microseconds. This energy heats plasma to millions of degrees and accelerates ions to velocities approaching 1% of light speed. 3I-ATLAS's orbital geometry amplifies these space weather effects. The comet's near-ecliptic trajectory means it will spend months cruising along the heliospheric current sheet, a vast, wavy boundary where the sun's magnetic field reverses polarity. Most comets cross this boundary quickly due to their high orbital inclinations, but 3I-ATLAS will repeatedly encounter regions of opposite magnetic polarity, creating multiple opportunities for dramatic plasma interactions. The European Space Agency's Rosetta mission provided our first intimate view of how solar storms affect comet environments. Even quiet comet 67P Churyumov-Gerasimenko showed remarkable sensitivity to solar wind variations, with plasma densities and magnetic fields fluctuating dramatically in response to relatively minor changes in solar activity. 3I-ATLAS, with activity levels orders of magnitude higher than Churyumov-Gerasimenko, should amplify these effects proportionally. Current sheet crossings deserve particular attention because they often coincide with stream interaction regions, boundaries between fast and slow solar wind that create compression waves propagating outward from the sunday. These regions can dramatically alter the pressure and magnetic field strength surrounding 3I-ATLAS, potentially triggering sudden changes in coma morphology visible from Earth-based telescopes. Visual signatures of space weather interactions appear across multiple wavelengths and timescales. Ultraviolet emissions spike when magnetic reconnection heats plasma in the inner coma. Optical images reveal kinks, rays, and disconnections in dust and ion tails as they respond differently to magnetic forces versus radiation pressure. Radio emissions might spike as accelerated particles generate plasma waves throughout 3I-ATLAS's extended atmosphere. The distinction between dust and ion tails becomes crucial during space weather events. Dust particles respond primarily to photon pressure from sunlight, creating tails that point steadily away from the sun regardless of magnetic field conditions. Ion tails, composed of electrically charged gas molecules, couple directly to magnetic field lines and can swing dramatically as those fields change orientation during coronal mass ejection passages. Mars orbiters might provide our first direct measurements of how 3I-ATLAS affects planetary space weather during the October 3rd encounter. If the red planet passes through the comet's plasma wake, instruments aboard Mars Express or MAVEN could detect changes in the planetary ionosphere or magnetosphere that would be impossible to observe remotely from Earth. Predictions for specific space weather events remain necessarily vague because solar activity follows chaotic rather than predictable patterns. We can estimate statistical probabilities, perhaps a 50% chance of at least one major coronal mass ejection encounter during 3I-ATLAS's inner solar system passage, but precise timing predictions exceed current capabilities in space weather forecasting. Amateur astronomers can contribute to space weather monitoring by rapidly reporting sudden changes in 3I-ATLAS's tail morphology or brightness. These observations provide crucial real-time data that professional observatories might miss due to scheduling constraints or weather conditions. Citizen science networks have proven particularly effective at monitoring such transient phenomena. The heliospheric current sheet structure varies with solar cycle phase, becoming more warped and complex during solar maximum. This increased complexity creates more opportunities for 3I-ATLAS to encounter magnetic field reversals, but also makes the specific geometry of each encounter more difficult to predict. The comet's path will depend on the detailed magnetic field configuration present during its passage. Educational opportunities abound for explaining space weather concepts using 3I-ATLAS as a natural laboratory. The comet's interactions with coronal mass ejections and solar wind structures provide concrete examples of plasma physics principles that are often discussed only in abstract terms. Visual evidence of magnetic reconnection and plasma acceleration makes these processes accessible to general audiences. What we must avoid is ascribing agency or intent to natural processes. 3I-ATLAS doesn't cause solar storms any more than a weather vane causes wind. The comet serves as an exquisitely sensitive probe of space weather conditions, revealing solar wind structures and magnetic field variations that would otherwise remain invisible. It's a scientific instrument disguised as a visitor from another star. The space weather predictions for 3I-ATLAS's solar system passage read like a cosmic weather forecast. High probability of magnetic storms, excellent chances for tail disconnection events, and spectacular opportunities for studying plasma physics under the most extreme natural conditions our local stellar environment can provide. Part 12. Science Payoffs at Terrifying Scale. The scientific return from 3I-ATLAS extends far beyond simple comet characterization. This ancient wanderer carries information that will reshape our understanding of planet formation, stellar evolution, and the chemical diversity of planetary systems across our galaxy. Every spectrum, every image, every measurement adds another piece to a puzzle that spans billions of years and thousands of light years. Interstellar chemistry benchmarking represents the most immediate scientific payoff. 3I-ATLAS's extreme carbon dioxide to water ratio of 8:1 establishes a new endpoint for comet composition diversity. Previous solar system observations suggested water-dominated chemistry was universal among comet-forming environments, but 3I-ATLAS proves that assumption catastrophically wrong. The 6 sigma deviation from normal comet chemistry isn't just unusual, it's revolutionary, forcing complete revision of models for ice condensation in protoplanetary disks. The implications cascade through planetary science. If 3I-ATLAS represents typical composition for comets forming beyond the carbon dioxide frost line, then planetary systems around different stellar types might show radically different volatile inventories than our water-rich solar system. M-dwarf stars, which comprise 75% of all stars in our galaxy, create very different temperature and irradiation environments during planet formation. 3I-ATLAS might be our first direct sample of M-dwarf system chemistry. Dusty plasma physics receives an unprecedented natural laboratory through 3I-ATLAS's enormous active coma. The comet's half-sun-wide atmosphere operates as a particle accelerator and plasma physics experiment on scales impossible to reproduce artificially. Magnetic field interactions, dust charging processes, and ion acceleration mechanisms studied around 3I-ATLAS will inform plasma physics research from fusion reactor design to interstellar medium modeling. The Rosetta mission provided detailed measurements of plasma phenomena around a relatively quiet comet, but 3I-ATLAS offers the opportunity to study these processes at extreme activity levels. Ion densities, magnetic field strengths, and plasma wave amplitudes should exceed anything measured at Churyumov-Gerasimenko by orders of magnitude, pushing plasma physics models into unexplored parameter space. Formation constraint studies using 3I-ATLAS's chemical fingerprint will help calibrate models of protoplanetary disk evolution around different stellar types. The carbon dioxide dominance suggests either formation at very large distances from the host star, beyond 3 astronomical units where CO2s can condense directly, or exposure to intense stellar irradiation, that preferentially removed water while preserving carbon-bearing volatiles. Each scenario implies different conditions in the birth stellar system. Formation at large distances requires protoplanetary disks more massive and extended than typical solar system models predict. Irradiation processing demands proximity to luminous stars that could provide the necessary ultraviolet flux. Both possibilities expand the range of environments where comet formation might occur, increasing estimates for interstellar object populations throughout the galaxy. Galactic archaeology benefits enormously from 3I-ATLAS's likely thick disk origin. Objects with ages exceeding 7 billion years sample stellar formation conditions from when our galaxy was younger, more chaotic, and chemically distinct from the present epoch. The comet's composition preserves isotopic ratios, elemental abundances, and ice chemistries from this ancient environment, providing direct constraints on galactic chemical evolution models. Thick disk populations formed during an era when stellar metallicity, the abundance of elements heavier than hydrogen and helium, was significantly lower than present levels. If 3I-ATLAS truly represents this ancient population, its composition should reflect lower oxygen, carbon, and nitrogen abundances relative to hydrogen, consistent with nucleosynthesis models for early galactic evolution. Interstellar object population statistics receive crucial calibration data from every confirmed detection. 3I-ATLAS, combined with Oumuamua and Borisov, establishes the beginning of a statistical sample that constrains models for how often stellar systems eject debris into interstellar space. Current estimates suggest every star system loses thousands to millions of small bodies during its evolution, creating a galaxy-wide population of wandering objects numbering in the quintillions. The chemical diversity observed across just 3 interstellar objects, Oumuamua's possible water ice, Borisov's carbon monoxide enhancement, and 3I-ATLAS's carbon dioxide dominance, suggests enormous variety in formation conditions across different stellar systems. This diversity challenges simple models of planetary system architecture and implies that habitable worlds might form under a much broader range of conditions than previously thought. Comparative planetology expands to truly comparative scales through interstellar object studies. Rather than comparing planets and moons within our single stellar system, we can now compare formation products from completely different stellar environments. 3I-ATLAS represents data from what might be an M-dwarf system, a binary star environment, or a stellar nursery with very different properties than the relatively gentle environment where our Sun formed. Methodology development for rapid interstellar object characterization will benefit future discoveries. The Coordinated Observational Campaign targeting 3I-ATLAS established protocols for international telescope coordination, data sharing, and rapid response spectroscopy that will streamline studies of future visitors. These techniques become increasingly important as next-generation surveys like the Vera Rubin Observatory begin detecting interstellar objects at rates of dozens per year. Public engagement through 3I-ATLAS demonstrates astronomy's unique ability to capture popular imagination while advancing fundamental science. The comet's dramatic scale, interstellar origin, and spectacular space-weather interactions provide natural hooks for science communication, inspiring the next generation of researchers while building public support for astronomical research programs. Astrobiology implications emerge from 3I-ATLAS's chemical composition and formation environment constraints. If carbon dioxide-rich ices are common in other stellar systems, they might provide different pathways for delivering volatiles to forming terrestrial planets. The carbon-rich chemistry could support different types of prebiotic chemistry than the water-dominated models typically considered for early Earth. The scientific payoffs from 3I-ATLAS operate across multiple scales, from fundamental physics of plasma interactions to galactic-scale models of chemical evolution. This single interstellar visitor carries information about stellar formation environments, planetary system architecture, and cosmic chemistry that would be impossible to obtain through any other means. We're not just studying a comet, we're conducting a comprehensive survey of conditions in an alien stellar system, preserved in ice and delivered directly to our doorstep after a billion-year journey through space. Part 13. Comparisons 1I Oumuamua and 2I Borisov. The Interstellar Object Hall of Fame consists of exactly 3 members, and they couldn't be more different from each other if they had been designed by committee to showcase the full range of cosmic possibilities. Each represents a completely different class of object, formation, environment, and evolutionary pathway, collectively painting a picture of galactic debris so diverse it challenges every assumption about planetary system architecture. First came Oumuamua in 2017, the astronomical equivalent of a first contact that left everyone more confused than enlightened. This cigar-shaped wanderer showed no detectable coma, no gas production, and no obvious comet-like behavior despite following a clearly hyperbolic trajectory. Its extreme elongation, unusual acceleration away from the Sun, and tumbling rotation created a mystery that remains unsolved nearly 8 years later. Theories proliferated like academic mushrooms after rain. Was Oumuamua a fragment of a tidally disrupted asteroid, a shard of exotic ice that sublimated invisibly in our infrared blind telescopes? Some researchers even suggested it might represent our first encounter with extraterrestrial technology, a hypothesis that generated tremendous public interest but found little support in the observational data. The Oumuamua controversy highlighted both the excitement and the dangers of studying interstellar objects. With limited observation windows and unprecedented phenomena, the line between legitimate scientific speculation and sensationalism can become uncomfortably thin. The object's rapid departure ensured that many questions would remain permanently unanswered, leaving room for speculation that continues today. Then came 2I Borisov in 2019, arriving like a cosmic palate cleanser after Oumuamua's confusion. Here was an object that behaved exactly like astronomers expected an interstellar comet should behave: obvious coma development, predictable gas production, and spectroscopic signatures that screamed dirty snowball from space. Borisov restored confidence in our understanding of comet physics while demonstrating that interstellar objects could be studied using conventional techniques. But Borisov carried its own chemical surprises. Spectroscopic observations revealed unusually high carbon monoxide abundances, not as extreme as 3I-ATLAS's carbon dioxide dominance, but still significantly enhanced compared to typical solar system comets. The CO-rich composition suggested formation in a colder environment than most solar system objects experienced, hinting at different thermal conditions in Borisov's birth stellar system. Borisov's nucleus remained more conventional in size estimates, probably a few kilometers across based on brightness modeling and direct imaging attempts. Its activity levels, while higher than typical solar system comets at similar distances, didn't approach the extreme gas production rates that 3I-ATLAS demonstrates. Borisov represented interstellar chemistry that was unusual but not revolutionary. The visibility timeline favored Borisov enormously compared to 3I-ATLAS. The comet remained observable for months from Earth-based telescopes, allowing detailed monitoring of its evolution as solar heating increased and then decreased during its solar system passage. Amateur astronomers could contribute meaningful observations, creating a citizen science campaign that engaged thousands of observers worldwide. Now 3I-ATLAS arrives to complete this bizarre trilogy, bringing chemistry so extreme it makes Borisov look conventional by comparison. The 8:1 carbon dioxide to water ratio pushes comet composition into territory that challenges basic assumptions about ice condensation in protoplanetary disks. Where Oumuamua was mysteriously inactive and Borisov was reassuringly normal, 3I-ATLAS is hyperactive in completely unexpected ways. The velocity comparisons reveal the dynamic diversity of interstellar space. Oumuamua approached at roughly 26 kilometers per second relative to the Sun, fast enough to confirm interstellar origin, but not extraordinarily so. Borisov moved at about 32 kilometers per second. 3I-ATLAS screams through our solar system at 58 kilometers per second when far from the Sun, making it the fastest confirmed interstellar visitor we've recorded. Orbital geometries paint three completely different pictures of galactic dynamics. Oumuamua followed a steep, highly inclined trajectory that carried it well above and below the ecliptic plane, minimizing its interaction time with planetary and solar wind structures. Borisov's orbit was moderately inclined, providing reasonable observation opportunities without the extreme space weather exposure that 3I-ATLAS will experience. 3I-ATLAS's near-ecliptic retrograde path represents the most dynamically interesting case: maximum interaction time with solar wind structures, multiple planetary encounters, and the highest probability for dramatic space weather events. This geometry alone makes 3I-ATLAS scientifically valuable, regardless of its unusual chemistry. The nucleus size constraints span an enormous range across all three objects. Oumuamua's dimensions were inferred from its extreme brightness variations during rotation, suggesting something between 100 and 1,000 meters in length, with an aspect ratio of at least 5:1. Borisov's nucleus remained unresolved, but appeared to be a few kilometers across based on standard comet brightness models. 3I-ATLAS pushes nucleus size uncertainty to its limits with Hubble's 5.6 kilometer upper bound that could accommodate objects as small as a few hundred meters. The disconnect between nucleus size and activity level reaches its most extreme expression with 3I-ATLAS, where a potentially tiny solid body generates an atmosphere comparable to stellar dimensions. Public narrative evolution across the three discoveries reveals how astronomical communication has adapted to the Internet age. Oumuamua sparked wild speculation about alien artifacts, partly because scientists were appropriately cautious about making definitive statements with limited data. Media and social media filled the uncertainty vacuum with increasingly exotic explanations. Borisov benefited from lessons learned during the Oumuamua episode. Scientists communicated more proactively about what the observations revealed, emphasizing the comet's conventional behavior while highlighting its genuinely interesting chemical properties. The result was more balanced coverage that maintained public interest without encouraging unfounded speculation. 3I-ATLAS represents the newest test case for science communication in the social media era. The comet's extreme properties, half-sun-wide atmosphere, ancient origin, unprecedented chemistry, provide natural hooks for public engagement while requiring careful explanation to distinguish genuinely unusual science from science fiction. Comparative analysis across all three interstellar visitors reveals the importance of statistical samples in astronomy. Any single object might represent an extreme outlier with little broader significance. But three objects showing such diverse properties strongly suggest that interstellar space contains representatives of every possible formation environment and evolutionary pathway. The chemical progression from Oumuamua's apparent inactivity through Borisov's CO enhancement to 3I-ATLAS's CO doi dominance maps out a continuum of compositions that spans from asteroid-like to extremely volatile-rich. This diversity confirms theoretical predictions that interstellar object populations should sample the full range of small body types ejected from planetary systems throughout galactic history. What emerges from comparing our three confirmed interstellar visitors is a lesson about making generalizations from limited data. Each object has confounded expectations in different ways, suggesting that our fourth, fifth, and sixth interstellar discoveries will probably surprise us just as thoroughly. The galaxy appears to contain small body populations far more diverse than our single stellar system ever suggested. The interstellar object comparison also highlights the value of rapid response observational capabilities. Oumuamua was discovered too late in its solar system passage for optimal characterization. Borisov received better coverage but still departed before many planned observations could be completed. 3I-ATLAS represents our best opportunity yet to study an interstellar visitor throughout its entire solar system encounter, from discovery through departure. As we await the next interstellar visitor, the three confirmed objects provide a foundation for understanding what kinds of debris wander between the stars and what they can tell us about planetary system formation throughout our galaxy. Each visitor carries messages from stellar neighborhoods so distant that their light hasn't reached us yet, making interstellar objects our fastest and most direct method for studying the chemical diversity of alien worlds. Part 14. What we'll watch through 2026. The next 18 months will unfold like a carefully choreographed cosmic ballet, with 3I-ATLAS pirouetting through our solar system while humanity's most sophisticated instruments document every twist, every leap, every moment of this ancient wanderer's brief performance on our local stage. The timeline reads like a greatest hits album of astronomical opportunities, each encounter offering unique scientific prospects that may not repeat for centuries. October 3rd, 2025 marks the opening act. Mars flyby at 0.19 astronomical units, roughly 19 million kilometers. From the red planet's perspective, 3I-ATLAS will blaze at magnitude 11, bright enough for detailed imaging and spectroscopy if Mars orbiters can be convinced to look up from their geology surveys. The European Space Agency's Mars Express and NASA's MAVEN spacecraft carry instruments potentially capable of detecting the comet's plasma environment, offering our first chance at in situ measurements of an interstellar visitor's interaction with planetary space weather. The Mars encounter geometry creates opportunities for triangulation observations, with Earth-based telescopes and Mars orbiters simultaneously viewing 3I-ATLAS from different angles. These parallax measurements could help resolve the persistent uncertainty about nucleus size and internal structure, providing independent constraints that don't rely on albedo assumptions or point spread function modeling. Solar conjunction looms as the performance reaches its climax. October 29th perihelion at 1.36 astronomical units places 3I-ATLAS at its closest approach to the Sun, when gas production should reach maximum intensity and the coma should expand to its largest extent. Unfortunately, the geometry conspires against Earth-based observers, positioning the comet nearly behind the Sun from our perspective, and making ground-based observations impossible during the most scientifically interesting period. But space-based telescopes don't suffer from solar glare the way Earth-bound observers do. Hubble has planned ultraviolet observations designed to probe atomic emissions in the innermost coma, where collision-induced fluorescence reveals information about gas densities and temperature distributions impossible to obtain at other wavelengths. These UV measurements will complement earlier infrared spectroscopy, building a comprehensive picture of 3I-ATLAS's atmospheric structure across the electromagnetic spectrum. JWST's post-perihelion observation campaign promises the most detailed chemical analysis of any comet in history. As 3I-ATLAS emerges from solar conjunction in November, the Space Telescope will repeat its earlier spectroscopic measurements to monitor how gas production rates and compositional ratios change in response to maximum solar heating. These comparisons will reveal whether the extreme carbon dioxide dominance represents intrinsic nucleus chemistry or results from preferential release due to surface effects. Venus geometry on November 3rd offers yet another planetary encounter, though at a more comfortable distance of 0.65 astronomical units. The encounter occurs in a different solar wind sector than the Mars flyby, potentially exposing 3I-ATLAS to different magnetic field orientations and particle densities that could trigger alternative types of plasma interactions. December 19th brings the comet's closest approach to Earth at 1.8 astronomical units, still more than the Sun-Earth distance, but close enough for coordinated ground-based campaigns using the world's largest telescopes. By then, 3I-ATLAS will have survived perihelion passage and begun its outbound journey, allowing astronomers to study how the coma contracts and evolves as solar heating decreases. The Earth encounter timing coincides with excellent observing geometry for Northern Hemisphere telescopes, potentially enabling amateur astronomical communities to contribute meaningful observations for the first time during 3I-ATLAS's visit. Citizen science networks have already begun preparing finder charts and observation protocols, hoping to engage thousands of observers in monitoring the comet's post-perihelion behavior. March 16, 2026 delivers the finale, Jupiter encounter at 0.36 astronomical units. By then, 3I-ATLAS will be operating under very different conditions than the inner solar system environment where most observations have occurred. The outer solar system space weather is dominated by high-speed wind streams and correlating interaction regions rather than the coronal mass ejections and current sheet crossings that characterize the inner heliosphere. Jupiter's enormous magnetosphere creates additional complexity for the encounter. If 3I-ATLAS passes through the Jovian magnetic field, its plasma tail could undergo dramatic restructuring as it transitions between solar wind and planetary magnetic control. These interactions might be observable from Earth as sudden changes in tail morphology or orientation. Spacecraft mission concepts continue evolving as 3I-ATLAS's trajectory becomes better defined. While no existing missions can be redirected to intercept the comet, feasibility studies for future interstellar object encounters benefit from understanding the observational opportunities and challenges that 3I-ATLAS presents. The lessons learned will inform planning for rapid response missions to future interstellar visitors. The extended observation timeline allows monitoring of physical processes that operate on different timescales. Nucleus rotation, if detectable, might reveal shape and spin state information through periodic brightness variations. Coma morphology evolution traces the response of gas and dust production to changing solar illumination. Tail disconnection and reconnection events respond to solar wind magnetic field variations on timescales of hours to days. Data release schedules from major observatories ensure that scientific results will continue emerging long after 3I-ATLAS departs our solar system. JWST observations typically require months of processing and analysis before reaching peer-reviewed publication. Hubble's UV spectroscopy involves complex calibration procedures that can extend analysis timelines by a year or more. Ground-based campaigns often rely on coordinated data sharing between observatories that can take additional months to organize and cross-calibrate. The Minor Planet Center continues issuing updated orbital elements as new observations refine 3I-ATLAS's trajectory. These updates are crucial for planning future observations and ensuring that telescope pointing remains accurate as the comet's high velocity carries it rapidly across the sky. Amateur astronomers and professional observatories alike depend on these ephemeris updates for successful observations. Public engagement activities will track 3I-ATLAS throughout its solar system passage, with astronomy education organizations planning special events around each major encounter. The comet's interstellar origin and extreme properties provide natural hooks for discussing topics ranging from stellar evolution to plasma physics, potentially inspiring a new generation of scientists and maintaining public interest in astronomical research. Archive observations will continue contributing to 3I-ATLAS science long after the comet disappears into interstellar space. Digital sky surveys have been imaging the comet's path for months before its discovery, and careful analysis of these archival data might reveal earlier stages of coma development that weren't recognized at the time. These precovery observations extend our baseline for understanding how 3I-ATLAS's activity evolved as it approached our solar system. The 18-month observation campaign represents humanity's most comprehensive study of any single comet, interstellar or otherwise. By the time 3I-ATLAS accelerates back into the void in late 2026, we will have accumulated more detailed measurements of an individual comet than any previous mission or observation campaign has achieved. The data will be analyzed and reanalyzed for decades, ensuring that this ancient visitor's brief appearance continues yielding scientific discoveries long after it's gone. Part 15. The real meaning of terrifying scale. As 3I-ATLAS accelerates toward its final departure from our solar system, carrying with it the accumulated weight of 18 months of human curiosity and wonder, we're left to contemplate what terrifying scale really means in an age when the universe reveals new impossibilities with each advancing year. Physical scale first, that gossamer atmosphere stretching 696,000 kilometers across space, wrapping half the sun's diameter around a nucleus smaller than most asteroids. The ratio defies earthly intuition. It's like discovering that a marble can generate a fog bank the size of Texas, or that a single grain of sand can cast shadows across entire continents. 3I-ATLAS forces us to recalibrate our understanding of how small objects can influence vast regions of space through nothing more than ice sublimation and solar heating. The coma's enormous extent creates interaction cross-sections with the solar wind that exceed anything in our experience. When coronal mass ejections encounter 3I-ATLAS, they're hitting a target area comparable to a small star, even though the source of all this drama measures less than Manhattan's width. The physics scales in ways that challenge our ability to model or predict, pushing plasma simulations into parameter regimes no laboratory could ever reproduce. Dynamical scale demands equal attention. 68 kilometers per second at perihelion, fast enough to cross the continental United States in less than 2 minutes. This isn't the leisurely orbital mechanics of planets or the predictable paths of familiar comets. 3I-ATLAS moves with the desperate urgency of an object that has already escaped the sun's gravitational embrace and seeks only to minimize its time in alien territory. The velocity carries implications that extend far beyond simple numbers. At such speeds, 3I-ATLAS experienced our entire solar system as a brief interruption in its billion-year journey through interstellar space. The 18 months from discovery to departure represent perhaps 1/10,000,000th of its total travel time since ejection from whatever distant stellar system gave it birth. We're witnessing the cosmic equivalent of a highway rest stop, a momentary pause in an odyssey that spans geological time. Temporal scale provides perhaps the most unsettling perspective of all. Multiple kinematic analyses suggest 3I-ATLAS belongs to our galaxy's thick disk population, implying an age exceeding 7 billion years. This wanderer may have formed when our solar system was nothing more than a diffuse nebular cloud, carrying chemical fingerprints from an epoch when star formation followed different rules and heavy elements were far less abundant than today. The comet has witnessed our galaxy's evolution through cosmic epochs we can barely imagine. It survived whatever catastrophe ejected it from its birth system, perhaps a stellar flyby, planetary instability, or the death throes of its parent star. It cruised through the void while our sun condensed, while planets formed, while life arose on Earth and evolved through billions of years of biological innovation. Yet for all its ancient heritage, 3I-ATLAS demonstrates the electromagnetic vitality that characterizes our modern universe. That half-sun-wide atmosphere isn't just expanding gas, it's a living, breathing plasma environment where magnetic fields twist and reconnect, where particles accelerate to incredible velocities, where the gentle but persistent pressure of starlight sculpts matter across distances measured in astronomical units. The plasma physics playing out around 3I-ATLAS operates on scales that humble human engineering. Magnetic field lines stretch and snap across volumes that could contain multiple Earth orbits. Electric fields build up and discharge with energies that make terrestrial lightning look like static electricity. Ion acceleration proceeds continuously across the entire coma, creating a natural particle accelerator that dwarfs anything we could construct on Earth. Solar maximum timing amplifies every dramatic possibility. 3I-ATLAS arrived not during a quiet solar minimum, when space weather remains relatively calm, but during our star's most tempestuous phase. Coronal mass ejections, magnetic field reversals, and high-speed wind streams create the kind of chaotic plasma environment that transforms predictable comet tails into spectacular displays of cosmic violence. The observational challenges match the physical extremes. 3I-ATLAS crosses the most star-crowded regions of our sky, requiring careful separation of comet light from the dense stellar background of our galaxy's central regions. Its rapid motion streaks telescope images. Its enormous coma confounds traditional photometry, and its interstellar chemistry resists easy interpretation using solar system analogies. Each measurement pushes instrumental capabilities toward their limits. Hubble's nucleus size constraint represents one of the most challenging small object observations the telescope has ever attempted. JWST's spectroscopic analysis ventures into compositional territory no previous mission has explored. SPHERICS's coma mapping required extending detection algorithms beyond their original design parameters. The scientific implications cascade across multiple disciplines and scales of understanding. 3I-ATLAS isn't just an unusual comet, it's a direct sample of interstellar chemistry, a probe of ancient galactic conditions, and a natural laboratory for studying plasma physics under extreme conditions. Every measurement constrains models of planet formation around other stars while revealing new complexities in processes we thought we understood. But perhaps the most terrifying scale of all is the scale of our ignorance illuminated by 3I-ATLAS's visit. This single object has revealed gaps in our understanding of comet chemistry, plasma physics, and galactic evolution that will require decades of additional research to address. It demonstrates how much we still don't know about the universe beyond our immediate stellar neighborhood. 3I-ATLAS forces us to confront the possibility that our solar system, for all its complexity and beauty, represents just one example of planetary system architecture in a galaxy containing billions of alternatives. The extreme chemistry, unusual dynamics, and ancient heritage of this visitor suggest that the cosmos harbors phenomena far stranger and more diverse than our provincial experience has prepared us to recognize. When 3I-ATLAS finally disappears into the void in late 2026, it will carry with it our measurements, our curiosity, and our humility in the face of cosmic scales that exceed human comprehension. The terrifying scale isn't just about size, speed, or age. It's about the revelation that the universe continues operating at extremes that challenge our most basic assumptions about what's possible. In the end, 3I-ATLAS serves as a reminder that we inhabit a cosmos where ancient wanderers can carry messages across billions of years and billions of kilometers, where tiny objects can generate phenomena on stellar scales, and where the space between the stars isn't empty void, but a vast ocean of possibilities we've barely begun to explore. The comet's brief visit leaves us with questions that will outlive everyone currently studying it, ensuring that 3I-ATLAS's legacy extends far beyond its physical departure. Sometimes the most profound discoveries come not from finding what we expected, but from encountering phenomena so extreme they force us to expand our definition of what the universe allows. And in that expansion of possibility lies both terror and wonder, the recognition that we live in a cosmos far stranger, more violent, and more magnificent than our earthbound experience could ever suggest.